In this video, we're computing the integral of 3 minus x squared all raised to the 3/2 power. And at first glance, you can tell immediately this is a trig substitution kind of integral. I'm going to make a substitution to try to build a single squared trig function inside those parentheses. That will simplify the exponent of 3/2. But as it turns out, we end up having to integrate a non-trivial trigonometric integral. And then the final conversion back in terms of x at the end of this integral requires the use of 2 additional trig identities. So I'm giving this problem an asterisk. It's definitely a challenge problem. We'll start things out with the trig substitution, and I'm going to let x be square root 3 times sine theta. And the reason I did this is because x squared gives me 3 sine squared theta, and then I can factor the 3 out, and that's dealt with. We also have to transform the differential. So dx is root 3 cosine theta d theta. And we're ready to transform the integral. And I'll just go ahead and move that root 3 from the differential out in front. So as we planned, we can factor a 3 out of these parentheses. But that 3 is going to be raised to the 3/2 power, and that means you cube it and then square root it. That gives me the square root of 27, which is 3 root 3. But when I multiply that by this square root of 3, that produces a 9 in front of the integral. And then inside these parentheses, I have a 1 minus sine squared, which is cosine squared. So then cosine squared to the 3/2, if I square root that, I get cosine, and then raise it to the 3rd power, I get cosine cubed out of this piece. Multiply by another cosine, and I've got cosine to the 4th. And when you have an even power of the cosine function, you really don't have any choice but to use an identity. And we're going to use the identity that cosine squared is 1/2 times 1 plus cosine of twice the angle. To use our identity, we have to split cosine to the 4th into 2 pieces. So that's cosine squared multiplied by cosine squared. Then we substitute in twice using this identity for cosine squared theta. That gives me 2 factors of 1/2. I'm going to pull that in front, and that's a 9/4. And I end up inside the integral with a 1 plus cosine 2 theta multiplied by itself. Now I need to expand this. And now my integrand is 1 plus 2 cosine 2 theta plus cosine squared of 2 theta. And again, the square of the cosine is a problematic term, and we're going to handle it by applying the same identity. This time, the cosine squared of 2 theta means our identity produces a 4 theta at the end. And I can clean things up a little bit in the integrand when I distribute the 1/2. I end up with a 1/2 that can be combined with the 1 out in front. That gives me a 3/2. So I have 9/4 integral of 3/2. Just lost a 2 for a second there, plus 2 cosine 2 theta, plus a 1/2 cosine 4 theta d theta. And each of these pieces can be done in one step. For the cosine terms, I'm going to have to use the chain rule backwards, so we have to adjust some constants. And I have 9/4 times 3/2 theta. And then for my first cosine term, I already have the derivative of the interior function 2 theta sitting out in front. That accounts for the effect of the chain rule. This integrates to sine 2 theta. So when I differentiate sine 2 theta, I get cosine 2 theta times 2, so it works. A similar thing is going on in the cosine 4 theta term, but I need to get a 4 out in front to prepare it to integrate, and that means dividing by 4 out in front of the entire thing. And so I end up with a 1/8 sine of 4 theta. And there will be a plus c on that, but we have plenty of work to do before we state our final answer. So at this point, we have the result of the integral in terms of theta, but we're not done until we get it in terms of x. And if I go back to my original substitution, x is root 3 sine theta, and that means theta is the inverse sine of x over root 3. And we can visualize this angle with a right triangle. This is going to be useful for computing trig functions of inverse trig functions. And here's theta, and it's the angle whose sine is x over root 3. That means the opposite is x, the hypotenuse is root 3. So the adjacent side has got to be a 3 minus x squared, all square rooted. Double check real quick that the Pythagorean identity is satisfied here. The square of the adjacent side is 3 minus x squared, plus the square of the opposite side. That kills the x squared. And I end up with a 3, which is the square of the hypotenuse. Okay, so that's ready, but the problem here is we can't directly sub in inverse sine of x over root 3 for theta because I have twice theta in this expression and 4 times theta in the last expression. Those have to be broken down in terms of trig functions of theta itself. And this is going to require two more trig identities. The sine of twice an angle, that's 2 sine theta cosine theta. So we can break that one down. What about the sine of 4 times an angle? Well, 4 theta is just 2 times 2 theta. So it's the sine of twice an angle, where the angle is 2 theta. So let's write down that next step. And in that last term, the trig identity, again, produces a factor of 2. So I can cancel one of those and get a 1/4. And then I have the sine 2 theta cosine of 2 theta. So we still have a problem with that last term. I have to break down again the sine of 2 theta into sine of theta and cosine theta. And then the cosine of 2 theta, well, there's an identity for that too. That's given by cosine squared theta minus sine squared theta. The sine 2 theta identity, again, produces a factor of 2, and I can cancel one of those factors of 2, giving me a 1/2 out in front. And I have a sine theta cosine theta multiplying cosine squared theta minus sine squared theta. Now I can start calculating all these trig functions of theta, where theta is the inverse sine of x over root 3 and is also visualized in this triangle picture. All right, we'll start things out by simply replacing the theta in this first term with inverse sine x over root 3. And that piece is essentially done. And then I have a plus 2 times the sine of theta. Well, the sine of the inverse sine of x over root 3 is just x over root 3. And then I have the cosine of theta, and I have to look at my triangle for this. The cosine of theta is root 3 minus x squared divided by root 3. And then my final term, that really ugly one, it starts with the sine of theta, which is again x over root 3. A cosine of theta, which again is root 3 minus x squared over root 3. And this is multiplying the square of the cosine of theta, which would be a 3 minus x squared over a 3 minus the square of the sine of theta, which is an x squared over 3. And at this point, I have a little extra room. I'll go ahead and start throwing in the plus c. I know there's an arbitrary constant of integration involved. Now, there's a couple instances where I have root 3 multiplied by itself, which gives me 3. Those can be cleaned up. And in the same step, I'm going to combine some like terms in the parentheses in that final term. So I've got 9/4 times 3/2 inverse sine x over root 3 plus, in the denominator of my second term, I have 2 factors of root 3. So I'm going to end up with a 2/3 here. X square root of 3 minus x squared. Then in my third piece, I have 2 factors of root 3 in the denominator times a 2 in the denominator. So I get a 1/6 out in front, but I can pull out a 1/3 out of the piece in parentheses as well. So I get 1 over 18. All the denominators have been taken care of, and I have an x square root 3 minus x squared. And in that last term, the numerators of those 2 fractions, I already pulled out the 3 from the denominator, and that's a 3 minus x squared minus another x squared, so 3 minus 2x squared. And we add in the arbitrary constant c. And we're out of room, so we're going to bounce to the next page. And we'll keep the 9/4 out in front for now. And I noticed the second term and the third term, they have this common factor of x square root 3 minus x squared. So we're going to factor that out. That leaves us with a 2/3 plus 1/18 times 3 minus 2x squared. And our plus c is still tagging along. And in the next step, I'll go ahead and distribute the 9/4 because we're getting close to the final answer here. So I have 27 over 8 inverse sine x over root 3 plus 9/4 x square root 3 minus x squared. And then when I distribute the 1/18 to the 3, that gives me 3/18, which is 1/6. Well, 2/3 is 4/6, so I end up with 5/6 for my constant. And then for that quadratic term, I end up with negative 2/18 x squared, which is negative 1/9 x squared. And we'll go ahead and cancel a 3 out of those denominators. And we're canceling that with one of the factors of 3 in the 9 up here. And I'll go ahead and write my plus c. And inside those parentheses, I have a 5/2 minus 1/3 x squared. And I could clear both of those denominators if I multiplied it all by 6. So I'm going to do that and divide by 6 out in front to compensate. Well, 6 times 5/2, a factor of 2 cancels and I get 15. 6 times 1/3, a factor of 3 cancels and I get 2. So 15 minus 2x squared. Then the constant out in front of that term, I'll cancel a factor of 3 there. It leaves me with a 1/8 out in front. And it looks like we're fully simplified here. And we've got our final answer. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left. Or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.